So let's start again. Little bit late. I got stuck in a couple of discussions. Anyway, the next step. Now we talked about all the data sets that are available, but sometimes the available data is not enough. You need more, and the question is how to get to more data. Of course, you can do more experiments, collecting more. You can have more patients coming in. But at one point, you can't create more data, and it may not be sufficient anyway. So what we do then is go to augmentation. So that is modifying the existing data in a way that it distorts it in different ways. These distortions can be shifting around. We can zoom a little bit, making different sizes. We can do rotations about the sample. Also, intensity variations you can introduce. Of course, color can also be if you have color data. You can also do shearing, so distorting it really bad. And on top of that, you can also add noise, blurring to simulate different acquisition conditions. So higher or lower dose acquisition, better or worse resolution of the system. And some examples of augmentations you can see here. So we have the original data of these two. So we have, this is a retinal image of blood vessels and its label. And when you do the augmentation, you can do, for example, an elastic. So you have this grid which you really shake around a lot. You can also do rotations on the data. And zooming, in this case it was zoom 0.75 in one direction and 1.5 in the other direction. So it was shrinking and stretching in two directions. This data comes from the database Drive, which is a database dedicated to retinal blood vessel images. It is free, but you have to contact the maintainers to get access. And these images were prepared by my master student, who is now doing the machine learning on the roots. What you can do, or what you not can do, is some transformations are not really relevant for the case that you're studying. So, for example, CT images of humans, you can't flip them too much. That would be, the head is always up. So, and other things, you can't scale the intensities too much because, for example, in tomography, the intensities have a physical meaning. And so, for example, the Hounsfield units, they are normalized to water, and then you have a scale based on that. And if you change the intensity, then you actually move away from what is real. For example, then the liver would have attenuation coefficients of bones, which wouldn't make much sense. And also, how much can you distort the image? You saw on the previous slide, I did some elastic distortion. How much are you allowed to do these distortions and still be able to recognize the features as what they really are? And what you can do for this is to use, in Python, is to use this image data generator, which is a part of the Keras package. A package I think you need to install. It's not in the environment that is provided on the GitHub. Usually it's only to install it using conda install Keras, and then you get it. I had some computers which went into some kind of conflict mess, and it was standing there for hours. So I hope for you that it's an easy install. On most of my computers it was. So I hope it will work, because also the exercises afterwards, they will be based on using this data generator. What it does is you set up the data generator with some interval limits. So if you look here, for example, the rotations are allowed to be within 30 degrees. The width shift range is 25% of the image size. Also the height shift. Shear range, that means shearing, so pulling it in different directions. So you would get rhomboids out of rectangles. Also zoom can be introduced, and flip and horizontal and vertical, they are disabled. So with this you can set up an environment for augmenting the data. Wait. I think I need to execute this one. I did. Okay, next slide. So looking now at MNIST data again, labeling number data is a pretty easy task. I mean, most people can read numbers, even though they are written with a very shaky hand, or with from someone who is not very good at writing readable. You can still recognize the numbers, with some few exceptions. So looking at the numbers, we load this data set. We have the original data on the top row, and then we have some augmentations. Here you can see this one was a bit shrunk and also displaced. This one was been made wider, this one moved a little bit down, and so on. So you can see here how the numbers are moving around, getting rotated, getting a little bit different stretch. So this already multiplied our data set by a factor 4. And that also gives you the possibility to work with more data in your training. So in particular, if you have unbalanced data set, you can use augmentation to boost the small data set, or the small fraction of the data. And with that, you get a better training on that part. Then we can look at some other data sets. In this case, we are looking at the CFAR data set, also from Keras. Keras has a lot of data sets included, or access to data sets. And if we look at that data set, you can see here we have different things. That one I actually can't see what it is. A truck, another truck with the tray tilted, some animal, a car, a bird, a horse, a boat, and a cat. And these images are now skewed around or messed up using this augmentator. In some cases it produces data which doesn't really make sense, so then you may have to tune the parameter range of the augmenter. So for example, these two, they're useless to recognize as a horse or as a car. So when you start doing this augmentation, it's also important that you inspect the data to see if it really produces what you want and what you need. Then now we are leaving the data and make a little step towards the machine learning techniques. And a baseline is method that you use as reference to compare other algorithms. It's a very simple algorithm. Some cases it can be just random guess. but it kind of simulates the worst case of what you can expect out of an algorithm. And mostly your algorithm should perform better than the baseline. There are cases when it actually performs worse, but then you're really on the wrong way. Let's take a look at one example. This is one about breast cancer. We have a model. It predicts breast cancer with more than 99% accuracy. The algorithm is saying, do I have breast cancer? And provide information about age, weight, and race? No. That's the predictor. This one has 99.91% accuracy to say no. And that's fantastic, right? No. Not really. So we have to look up for something that actually takes this very small fraction and treats this correctly. There is another fun example saying, will I meet Santa today? And it has, well, 1/365% accuracy to get the right answer. So also that one is not so good. So let's start with a dummy classifier. And the classifying strategy is to take the most frequent is the one that we say is the prediction. So if we have this data set, we have 1, 2, 3, and we say healthy, healthy, healthy cancer. We see that there is an imbalance. The majority says it's healthy, and we train it. And after that, we try to do a prediction, and what do we get? Well, of course, as we have most frequent, all samples are healthy, is the prediction. So it's not a very smart algorithm, but it can be used as a baseline to check the properties of other algorithms. So it must be better than this one. Looking at the dummy classifier on MNIST data, then we load the MNIST data, and looking at that, and we can see we have our numbers. We can see there is a number distribution. The histogram is a little bit shifted, so the 0 is this bar, this is the 1, and then we see here we have the numbers with their correct labels as we load them. And let's train it, again using most frequent. We use 24 images and the corresponding 24 labels, and that went well. And then we try doing a prediction based on the first 10 images. And it says, well, the images are all 1. But if we go back, let's see, no, wait. If we go back, we see they are definitely not 1. But now is the question, why are all 1? And of course, as you have seen, using this algorithm that we used, most frequent, we get the histogram again, and we can see that, well, 1 is the most frequent, and that is now our prediction from this algorithm. So let's try on other images, or look at these numbers. We can see that it's a 5, but it's predicted 1, it's a 0, it's predicted 1. Yay, we have a 1 and really predicted a 1, so fantastic. One is right at least. And so it goes on. Pardon? Did 9 get a 9? I don't think so. 9 is a 1. Yeah. So let's see. Something is not doing right. Yeah. So, a different algorithm. Now we actually go into one typical machine learning algorithm, which is called nearest neighbor. And this algorithm is looking at a collection of features and saying the one sample in my training data that is closest to the one that I provided is giving it the class. And here is an example taken from John Ross' image processing handbook. And you can see here the segmentation line is going pretty zigzaggy around. And all data within the pink region is closer to a red dot, while all the ones in the blue region is closer to a blue dot. The example here is using single nearest neighbor, or in this case, where you have a more consequent line, is having, let's see, 9 neighbors. So then it's actually looking in a neighborhood, the 9 closest items, out of those, the majority gives the class. It could happen. Here you can see there is a lot of blue dots, and they provide the island. So they probably are sufficient. This little cluster probably has 4 or 5, and that gives you the majority to provide the island. So it's really a non-linear classifier. Before no, we haven't done segmentation yet, but normally the basic segmentation, you set a threshold. If it's above, it's class A. If it's below, it's class B. This one can do it a little bit smarter. Yes? Well, it's more like if you have a bunch of dots. Oops, let's see if I can create some dots. Yeah. So, and then we have here. These belong to class A, and these belong to class B. And then it's looking in this area. If we have a dot about here, oh, that was too close. That one would always be classified as this class. But if you have something that is a little bit closer to this one, if you have nearest neighbor equal to 1 for one element, then this class would win. If you would have nearest neighbor for 3, then you would look at, okay, you have 2 neighbors out of that class, 1 neighbor out of that class, okay, that class win. So it's about looking at some distance, and of course you need to look at which kind of metric you use to define the distance, which I actually don't know what they do in the background in these algorithms right now. I have to look it up. But in principle, it's about computing the distance to the neighborhood features, and then from that, taking the closest. But yes. Then you change. So it's when you increase the number of neighbors, it gets more robust. Single, as you can see here, is getting a very interesting path, oops, I'm drawing a lot. It's getting you a very strange separation line. If you have, the more neighbors you have, the more clear the separation line is. Even though there can be that you have some blues on this side and some reds on this side, but you have a much clearer line between them. So that's a way to handle noise in the measurements. So I will come back to that one on a later lecture. Just to continue, let's load the data again. We have our numbers. Let's do the training. Let's do the training now. That's done. And now we do a prediction. And we get now different numbers for the different digits. And looking at the result, you can see that now we predict really good. We have a 5, it should be a 5, and it predicts a 5, a 0, it predicts a 0. there's only one problem now in this. We got 100% fit. Sounds great, doesn't it? But the problem is we have used the same data now in the test as we did during the training. And of course, that will fit 100%. To do the test, you need to take a different data set, which doesn't overlap with the one you used for the training. Otherwise, you will do kind of cheat yourself and you will think you have something fantastic, but it's not, because it's really going to do what you have trained it to. So the only way to do a good testing is to have split your data into two parts. One part is for the training, where you use a lot of data, and then you have a smaller fraction, often discussed how big this fraction is, say 10–20%, which you use for the testing to see how good you actually perform. So, looking at some other ones, now we look at a test with a different region, different part of the data set, and now you can see here it should be a 2, but now it predicts a 3, it should be a 4, it predicts a 1. Here we have a hit. This one apparently looks more like a 7, and the 7 looks apparently like a 1. So now it's not so good anymore, and that is what happens when you start testing with the right data set. If you have a good predictor, it will anyway produce good results. If you have a bad one, the result may vary. And a way to get an idea how good your predictor is to use the confusion matrix, which is presented like this. If you have just a true-false matrix, so we have in this case 165 samples, it should be true. So when you have actual true and predicted true, you put the numbers in here. Actual true, predicted false, you see here that it's not so good maybe, so it's 10 out of 50, 10 to 50 is the error here, and also you can do the same actual false, predicted true, you get some error, you predicted false for actual false, then you get 100. Ideally, the confusion matrix should have large numbers along the diagonal and small values on the areas outside. So now let's take a look at what does the confusion matrix look like for the data we fitted using the nearest neighbor on the numbers, and it takes a little while to compute it, but here you can see the resulting confusion matrix, where you can see, well, the diagonal kind of is dominant, but there are some cases that are confused. So 1 can apparently be confused with 2's. Here you have 4 to 9. Makes sense. If you make a sloppy 4 or sloppy 9, it could be interpreted as a 4. And so on. So here you can see which are the, say, weak combinations. The accuracy is not very good, so we are at 56%. Random guess would be 50%. So we are a little bit above the random guess. Ideally, you would like to have something like 90–95% accuracy.
Would a random guess be 50%?
Well, no, sorry. That would be something else here in this case. Sorry. If you have true-false, it's 50%. Here, it would be something else. I haven't computed it. And, well, that was the end of this part. Today's exercises, I uploaded them yesterday evening. It is essentially going through these examples, and then in the end, I want you to use real data and compute the confusion matrix for the real data, and then you make an augmented data set based on a fraction of the data and create a data set which is the same size as the original data, and then compare the confusion matrices for that. The exercises I have prepared in a way so you load, I guide you through what you need to work with, and in the end you have to put those blocks together, and I hope you can work with that. The data sets used are from lung CT slices, and you can see some healthy samples and some malign samples. And well, that was it for today. And well, then we can go on with the exercises afterwards.